This is Dr.D Govardhan, Professor in Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is derivation for frequency and time period of compound pendulum. A compound pendulum is the simplest form, consists of rigid body suspended at O vertically and oscillating with a simple amplitude under the action of force of gravity. At some instant, let the position of the rigid body be its extreme position as shown in figure. Let M be the mass of the pendulum, O is the pivoting point at which the pendulum oscillates or suspends vertically in downward directions. H is the distance between the pivoting point and the center of gravity of the pendulum. If the pendulum is given small angular displacement theta from vertical position or the axis of the pendulum, then the moment of the couple tending to restore the pendulum in equilibrium position is given by resolving the forces. One is along the axis, one more is perpendicular to the axis. Along the axis is mg cos theta. This it is the balanced with the reactions at which the object is suspended. The mg sin theta, it always tends to move the body towards its equilibrium position. So which is given by, the axial force is given by mgh sin theta. Since the angular displacement is very small, hence sin theta is equal to theta. Hence the modified equation of becomes mgh theta. Let I naught be the mass moment of inertia of the body about O, alpha be the angular acceleration of the body. Now the disturbing moment due to the angular displacement is given by I naught alpha. Equating these two moments, that is mgh theta equal to I naught alpha, where I naught is representing the mass moment of inertia of the pendulum at its pivoting point to O, alpha is the angular acceleration. Then by using these two equations we got alpha is equal to mgh theta divided by I naught now. So the time period for simple harmonic motions is given by 2 pi into under root of displacement divided by acceleration, or 2 pi divided by theta by alpha, which is equal to 2 pi into under root of theta divided by mgh theta divided by I alpha. On simplifications we got 2 pi I naught divided by mgh. Now the frequency of the motion is, it is the reciprocal of time period. It is equal to 1 by 2 pi under root of mgh divided by I naught. The above formula for the periodic time, that is frequency of motion, may also express in terms of radius of gyrations by using the fundamental of theory of parallel axis. The mass moment of inertia of the pendulum about O, I naught is given by Ig plus mh square, where I naught is representing mass moment of inertia of the pendulum at a pivoting point O, G is representing mass moment of inertia of the pendulum at its center of gravity, M is the mass of the pendulum, H is representing the distance between the pivoting point and center of gravity. So it is equal to Ig, that is the mass moment of inertia of the pendulum, at its center of gravity is given by mk square, where k stands for radius of gyration, plus mh square. So just m is the common term. Then the simplified equation is m of k square plus h square. Now substitute the values of I naught in equation number 3. The period time for simple harmonic motions theta is given by 2 pi into under root of I naught divided by mgh, which is equal to 2 pi into under root of m into k square plus h square divided by mgh. On simplifications, we got it 2 pi into under root of k square plus h square divided by gh. The frequency of pendulum is given by 1 by t, that is the reciprocal of time period, which is equal to 1 by 2 pi under root of gh divided by k square plus h square.
Like, share and subscribe. Hit the bell icon for more updates.